Hello everyone, my name is Sam Matloop. I'm a PhD student in the College of Engineering and Computer Science at the University of Central Florida. And this presentation is for COT 6410, Computational Complexity. And it's a talk about a research paper that I have selected during the semester titled Quantum Approximate Optimization Algorithm for Bayesian Network Structural Learning by Vicente and others. First thing first, I'm going to give an introduction to Bayesian network, explain what Bayesian network is, and talk a little bit about it, and then we'll give an introduction to quantum computing, very interesting topic, and then we're going to talk about the quantum and Bayesian network. Then we'll discuss the author's contribution, results that they have gotten from their experiment, and the conclusion. And I will end up the presentation with a few suggestions that, in my personal opinion, it would extend the contribution of this paper. So, what is Bayesian network? Bayesian network is one of the artificial intelligence probabilistic algorithm that uses a probability to anticipate and predict an event. Some of the problems that Bayesian network models could have one variable or could have multiple variables. These variables also called heuristics or observations. It just basically things that affect the prediction process in the algorithm and Bayesian network algorithm. Also, Bayesian network could be represented by a directed acyclic graph in which the nodes represent variables and the edges represent the influence of the nodes that the edge is connecting. Some problems when we try to model it with Bayesian network, we actually don't have a clue how the variables affecting each other and influencing each other. In which and in similar situations, we're going to have to go through all possible structures and study them and try to get the best, the optimal structure that can get us the best accuracy. And that's what the Bayesian network structural learning exactly is. It's just an optimization algorithm that go through all possible structures and get us back the optimal solution or the optimal structure that we can use in the model to predict future events. The problem seemed to be trivial for few number of variables if you think about it, because if we have only one variable, we only have one structure. Done. But if we have uh, two variables, we actually have three structures. And if we have three variables, we have 25 possible structures. The next slide, let me get to the next slide, shows a table that actually shows that increasing the number of variables or with increasing the number of variables shows that the number of possible Bayesian network structures increases as well, but exponentially, making the algorithm takes an exponential time before it can return the optimal solution or the optimal structure to us. And therefore, this optimization problem is an NP hard problem, and that's what has been proved by many. Quantum mechanics has received considerable attention in recent years, and quantum mechanics stems from the quantum phenomena, superposition, and entanglement. To understand superposition, we need to talk just a little bit about the qubits or quantum bits. Quantum bits or qubits are the basic units of the quantum information. And just like bits, how bits can hold two states, so is qubits. It can hold two states. So qubits could be either in state 0 or could be in state 1. With one major difference between qubits and the classical bits, that the qubits can also be on both states at the same time. So therefore, qubits could be in states 0 and 1 at the very exact same time. Given the quantum mechanics its power, this phenomena that is being in different states at the very exact same time called the superposition. on the other hand, the entanglement is just the uh, description um, to the connection that two particles can have um, on each other in a way that although they're very far away from each other, but if one particle changes property, then the other would change as well. And that's entanglement. To illustrate the importance of the superposition, let's take a very simple problem that is trying to find the path to exit out of the maze. So starting from the start point in the maze, if we're using the classical approach, we would be trying to explore all the paths until we get or we find the path that can exit us out of the maze, but during which we're gonna have to do a lot of backtracking and we're gonna have to really explore and spend a long time until we get to the path. While if you're using the quantum approach, then we could be exploring multiple paths at the same exact time because of the superposition, leading to a shorter time to find the shortest path to get us out of the maze. All right, so in order for us to be able to solve the Bayesian network structure learning problem using the quantum approach, we need first to convert this problem and take it from the classical realm to the quantum realm. The authors of this paper used the quadratic and constraint optimization algorithm, the QUBA, to convert the Bayesian network problem to a quantum problem. The QUBA um, comprises of a lot of calculations to calculate and compute the Hamiltonian variables such as the h-score, h-max, h-trans, and so forth. These Hamiltonian variables will be later on used to calculate the cost function. So once we get this problem or the Bayesian network problem converted to a quantum problem, now we can use a quantum algorithm to solve the problem. The authors of this paper decided to use the quantum approximate optimization algorithm QAOA to solve the Bayesian network problem. Farhi and others defined the QAOA as hybrid algorithm between the quantum and the classical ones. Vicente and others used classical approach to calculate cost function and the expectation value in each iteration. The QAOA uses a quantum parametric circuit that includes multiple layers, as we can see in the diagram. The initial state is a superposition of all possible computation states, while each layer describes two different operators that encodes the cost function which will be optimized. The main contribution for this paper is the fact that the authors use the quantum approximate optimization algorithm to solve the Bayesian network structure learning problem. According to the authors, at the time when they wrote the paper and did the experiment, no one has attempted to use the quantum approximate optimization algorithm to solve the Bayesian network structure learning problem. Alright, so the results of the experiment. The outcome of the experiment that the authors implemented reached to a comparable result to other experiments using a different quantum algorithms. The authors experimented in increasing number of layers to get a better answer, but the authors claimed tuning the alpha variable gave same answer with lower number of layers. Also, the authors confirmed through their experiment that the QAOA is resilient to the noisy intermediate scale quantum media that they um, experimented with. There are a few observations that I put on the slide, but because of the time constraint, I will only mention one. And that is, I really hoped that the authors would have included some information about how much time did it take to solve a Bayesian network structure learning problem using their quantum approach. All diagrams that I could see in their papers were showing the QAOA performance. And with this, I conclude my presentation. I thank you very much for your time, and I think I have a couple minutes to answer some questions that you may have.